Hello wonderful person, this is Anton, and today we're going to discuss a somewhat bizarre discovery coming from yet another comet in the solar system. A comet that for once is not 3I Atlas, but that actually exhibited something that's even stranger, and something that at first was kind of difficult to explain. In this case, this comet appeared to have completely reversed its rotation. Or in other words, it didn't just slow its rotation, it appears to have completely stopped and then reversed its spin entirely. And though we very often think of comets as basically these dirty snowballs, but also objects that are kind of static, that eventually evaporate and possibly leave nothing behind, in this case, the comet known as 41P or Tuttle-Giacobini-Kresák is now showing us that these objects are some of the most dynamic and some of the most unstable bodies in the entire solar system. But more importantly, understanding why this happens and, of course, how this happens, has now potentially solved one of the long-standing mysteries in astronomy. Specifically, why we see so few small comets compared to what our models predict. And so let's talk about this new study in a little bit more detail, but first let's talk about the comet and the initial discovery back in 2017. Because Comet 40P, that we can actually shorten to TGK for its three main founders, made the closest approach to the Sun back in early 2017. Here's a picture from March 2017 taken by Keith Scherer. And it was actually during this approach that researchers noticed something somewhat bizarre. At this point, the comet was rotating every 20 hours. But by May, just 2 months later, the rotation has dramatically slowed, with the comet now spinning every 53 hours, or more than twice as slow. But the real surprise came from the Hubble Space Telescope, and specifically the archival data that was recently analyzed by David Jewett and reported in the study you see right here. And he actually has another earlier study explaining a lot of this that you can also find in the description. And while in essence the analysis here revealed that by December 2017, or approximately 9 months later, the rotation period had shortened again to 14.4 hours. And the thing is here, mathematically, this only makes sense if the comet basically did a kind of a U-turn. Or basically, if its rotation at first slowed completely, with the comet then spinning in the opposite direction. This is essentially what you're seeing in this graph right here. But I guess the obvious question is, so how can such a massive object basically stop completely and then start spinning in the opposite direction? And the answer here lies in outgassing, and specifically outgassing torques. Today, based on many different observations, we know that quite a few comets possess the ability to release a lot of gas. And specifically through phenomena very similar to a typical volcano, although here we usually call these cryovolcanoes, because instead of releasing lava, they release huge amounts of water. And so as the comet approaches the Sun, its ices, which usually contain carbon dioxide and water, begin to dramatically sublimate and create these massive eruptions. This usually happens very violently, producing lots of different jets, and something resembling a geyser. And so if these jets are positioned unevenly, and especially in certain positions on the surface somewhere along the equator of the comet, they then start acting like these tiny rocket engines. And in most cases this produces a kind of an acceleration, causing the comet to slightly change its orbital parameters, shifting its orbital positions, but sometimes this creates a very strong reaction force that starts pushing against the nucleus and starts affecting its spin. And because this comet, 41P, is relatively small, possibly about 500 meters across or about 1500 feet, here these jets have a very large effect on its angular momentum. Here this is usually measured using something referred to as dimensionless moment arm, which essentially tells us how much of the gas's momentum is actually being used to spin the comet. And so this recent study essentially does a really good job explaining all of this, even though the observations are coming from 2017. But interestingly, this is not the only such comet and not the only such observation. Okay, technically this is the first time ever we observed a full reversal, but we have seen this break-in effect before. And the most famous one is from this comet known as 103P Hartley 2. This is a comet that was thoroughly studied back in 2010 and even visited by the Epoxy mission. And this is why we have this beautiful picture of this comet. And better even, we have a time-lapse showing us what this comet looks like from several sides. And while in this image you can even see these volcanic eruptions happening on the edges of this comet. And during its 2010 approach, it slowed its rotation from 17 to 19 hours in approximately 3 months, so not as dramatic as Comet 41P, but still quite significant. Technically, 41P changes rotation at least 10 times faster. And we've also seen something very similar in other small nuclei, such as the Comet 46P. This comet was tracked and measured by the Arecibo Observatory back in 2018, and has been studied quite extensively during this time. Here this is just slightly bigger at 0.6 km in size, or about 1700 feet, but it seems to have experienced a somewhat similar spin down. And so it looks like a lot of these very small hyperactive comets seem to be susceptible to these effects and seem to change their spins in just a few months when they approach the Sun relatively close. Although obviously the effects of this decrease dramatically if the size of the comet is much larger. Although here, just as a quick side note and I guess slight clarification, in most of these cases we don't really see the actual spin. As in, except for this one example, we don't really see the rotation of the body, and we only see variations in brightness as the comet rotates. And so here the period of rotation is established by looking at the periods between brightening as the comet rotates and reflects the sun. And so in the case of 41P, here there were actually two possible solutions. So either this comet reversed its rotation, or for some reason continued rotation in the same sense, once it first slowed down completely. And in this particular case, David Jewett argues that the reversal seems to be the most likely scenario. And that's because this data fits the smooth mathematical curve consistent with the sun being the source of the torque. But technically, it can also be that other scenario where the comet first stopped, but then for some reason restarted its rotation. That though doesn't really make as much sense. But as I mentioned before, this observation and this explanation also solves a major mystery when it comes to comets. So this is not just some kind of a space curiosity, it does address why these small comets seem to be missing from the solar system. And the mystery here actually comes from the observations by the probes like the New Horizons probe that captured several images from the Kuiper belt. So for example, objects like Arrokoth, or even Pluto itself, seem to contain a lot of craters on the surface, suggesting previous collisions with objects that would actually become comets if they came close to the sun. In other words, we expect a lot more small comets than we actually observe in the inner solar system. Or basically, if you count all of these craters, and if you count the amount of small comets coming close to the sun, something doesn't actually add up. A lot of them seem to be missing. But here, the behavior from 41P suggests that a lot of these small comets may actually spin themselves apart, or essentially they start spinning so fast as a result of these emissions that with time they just fall apart completely, leaving almost nothing behind. And so as they get smaller because of this outgassing, the torque becomes even more powerful, with the comet eventually reaching rotational instability. And so for a typical comet coming from the Kuiper belt, if its rotational period is less than 4.7 hours, this is for a typical comet of a typical size, it will simply fly apart because its own weak gravity cannot hold it together. And in this case, for 41P, it actually might be on a somewhat similar path. If it continuously evolves its spin, similar to the rates observed in 2017, it could actually reach the same breaking point and undergo a dramatic breakup in just a few decades. And we might be able to even see all of this sometimes in 2027. That's when this comet is going to approach the sun again, and when it might experience something similar involving these massive volcanoes. But in summary, this comet is actually pretty exciting and has officially showed us something we never really knew existed. It basically showed us that sometimes comets can spin so fast that in theory they can fall apart, and this is why maybe there are not a lot of comets in the inner solar system. And so when it comes close to the sun in 2027-2028, we might be able to prove this hypothesis and actually witness a destruction of a comet from basically spinning too fast. But until then, or until some other discoveries about comets, check out some of the previous videos on the 3i Atlas or some other comets in the description below. Thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining the channel membership that grants you early access and a few more things. You can also support this channel by buying the wonderful person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.